Well, what do we think? It's 1:30. Should we give people another minute or two? Or? I think people are still kind of coming in. All right. While we're waiting for folks to come in, can anybody identify these two paintings? Anybody? But okay.
Sailors, right?
On the right, Rembrandt, Anatomy Lesson of Dr. Tulip. Anatomy Lesson of Dr. Tulip. Yeah, Rembrandt. And then on the left, anyone recognize what's on the left? I'll give you a hint. We're all really glad that what happened in that picture happened. That is the first operation under anesthesia in Boston, yeah. The first operation using ether with everyone standing around a gog that it was working and waiting for the patient to jump up. I know. Yes, fun fact, there was actually not the first operation. There was a dentist who tried it first. Okay. Is anybody else walking up from out there? Yeah. All right. Well, how about we get going? If anyone else joins, they join, and we see where we go from there. So thanks for coming, everybody. I'm Stephen Bedrick, and I'm an associate professor in DMICE. I will be telling you all today about biomedical applications in NLP, with including some discussion of some interesting work in progress. So our plan is I'm going to tell you a tiny bit about me, but most of you already know me, so I'm not going to talk about that very much. And then, as is tradition for my summer seminar series for all of our interns who are joining us, I'll be talking a little bit about overview of what natural language processing is about as a field, and how it fits into biomedical research and practice. And we're going to dig in a little bit more about how we do NLP, different methods for NLP pretty quickly. And then because it's 2024, we will be talking about large language models, and I'll be telling us about using them, telling everyone about the time we tried to use it to summarize clinical documents, and how that worked. Okay. So about me, my PhD is in biomedical informatics, and then I did my postdoctoral training specifically in natural language processing, and the HLT stands for Human Language Technologies, which is sort of a slightly archaic umbrella term that includes speech recognition and OCR, optical character recognition, and other kinds of technologies that work with language. The boundaries are very, very, very blurry. And today I'm an associate professor here in DMICE, and then my research through a clinical lens, because informatics is interdisciplinary. When we look clinically, I work on computational analysis of notes, EHR notes and text, especially clinical notes. And we do this I do this for things along the lines of cohort discovery, so identifying populations of patients that meet certain criteria or have certain properties. We done work on data quality and analyzing EHR notes for implementation science and training purposes. And then my other sort of hat is applications of NLP for speech and language disorders. And in that world, I work on assessment and screening of, say, aphasia and autism spectrum disorder and other things along those lines. And I've also done a lot of work in augmentative and alternative communication. So that's communications technologies to help people with different kinds of speech or motor disabilities that make regular communication challenging. And then shifting to a computational lens, I work on areas like information retrieval, training and adaptation of language models from back before we called them large language models, when they were just regular language models, and document representation, how to do speech recognition on low resource data, meaning data where we don't have a lot of training data. So clinical samples where you might only have 100 recordings of someone with a certain condition, as opposed to the hours and hours and hours that we would like to have for normal ASR research. And then the last one was evaluation, how we actually measure and evaluate NLP tools, or any of these kinds of tools. So why do we even want to use computers to analyze language? And my really glib answer for that is that humans use language for everything, right? That's sort of what when we talk about what defines humans as different from other primates, usually like the thing everyone kind of settles on is we have language and other primates don't. And when we talk about other animals and wonder whether they're sentient or not, usually it comes down to our whales talking, our bats talking, right? Our birds that use language, are they really using language? So language is kind of the distinguishing thing about humans, and we would like our computers to also be able to use language. And so there's a large variety of application areas. So question answering, right? When you type in a question to Google and get an answer back, sometimes in the form of a narrative answer, other times recognizing it as a simple factual answer and mapping it to the factual answer. Information retrieval, right? Search engines like PubMed fall under NLP. And then within PubMed, a number of features of a modern search engine also are powered by natural language processing. So this is the old interface to PubMed before they redesigned it and hid this really useful feature, but it still has it on the side, a little sidebar of similar articles. That's a fairly simple NLP model that generates that. Pro tip, it is still there. It's just you have to scroll to the very bottom of the abstract page and click a few things to make it appear. They are, anyway, it's a long story. Automatic summarization, which is very germane to what we're talking about today. So we might have a long news article with a lot of detail and might like to get a small summary, so you don't need to read the whole thing. Spam filtering. Spam filtering is one of the first commercial applications of sort of modern statistical natural language processing. And then of course, machine translation, which I think if most of us have probably used at one time or another. It was also one of the very first tech applications of language, computers to language. And it's come a very long way now. Frequently used, it's good enough that people even use it when they don't speak when they don't speak either of the languages and are willing to trust it blindly, perhaps when they shouldn't. In terms of more applications, we'll be talking a lot more about healthcare applications, but legal discovery and compliance review is a big application area for NLP. Searching through 1 million emails from Enron to find out which ones are about the insider trading or the current energy market manipulation fraud. And then of course, natural language interfaces, being able to talk to computers using natural language and have the computer hopefully understand what you mean. And that has led, of course, to chatbots, right? So we've all seen customer service chatbots like the one on the Alaska Airlines website. Currently, those have come a long way and have much more powerful capabilities. Where we can ask them more general questions and get much more useful answers, ask silly questions and get silly answers. These have come a very long way and now are finding themselves being used in a lot of new areas, and we're, as a result, finding a lot of problems with how they work. I don't know if anyone remembers the Microsoft's ill-fated Tay chatbot, which was a few years ago that they had to take offline after, I think, less than 30, it was within 24 hours, because the internet turned it very racist very quickly. This did not deter Microsoft. A few years later, they tried again with Bing, with similar chaotic results, which got a great deal of press coverage at the time. With their attempts to fix it, got further press coverage. Various people in the NLP community did try to warn Microsoft that this was a bad idea. I'm actually confused why they did Bing the way they did after the Tay debacle, because I know from people inside Microsoft that had a big chilling effect on chatbot research at the company. But anyway, and then in recent months, we've seen unholy and misguided attempts to combine all of these: chat, question answering, and search, right? With results. I don't know if anyone saw this that Google was doing a few weeks ago, where it was advising us to add glue to our pizza sauce. And then as language technology is being used in more and more places, I saw this one on Amazon a little while ago, using it to displace repetitive work that previously would have been given to humans. Now we can give it to employees to get not very helpful product names. I'm glad that this comes in brown as well as perhaps, I was hoping for gray, but whatever. Okay, so that's sort of a whirlwind overview of applications for NLP. We can kind of make a taxonomy here, and I say we, this is actually David Smith's taxonomy, of three kind of main ways we use language technology. And one is to go from analog data to digital data. So that'll be speech recognition or optical character recognition, scanning a document and getting back out the text and something you can edit. Language to data, right, where we take, say, a news article and extract out a delimited list of people mentioned in the article, right? So taking unstructured data and making it structured. And then language to language, where we have linguistic input in, linguistic input output out. I've added this taxonomy image because in recent years, text to image has become actually a surprisingly capable modality. So how do we use this stuff in biomedicine? A few major areas of use in biomedicine include analyzing scientific literature. So I showed PubMed earlier. You may not know this, but the National Library of Medicine has actually always been at the forefront of NLP research and development for applying these technologies to help manage databases of medical articles and help people find medical information. So things like literature, helping with literature reviews, doing medical question answering, knowledge discovery, so identifying out of 1 million articles, which maybe there's some genes that are mentioned that we don't realize actually are related, but if you could read all 1 million articles, you'd be able to recognize a pattern, that sort of thing. And of course, summarization and translation play a role here as well. If you have information you want to make available to, say, providers who maybe aren't speaking English as a native language, something that could translate abstracts into Spanish or something like that could be helpful. And then, of course, clinical text has its own set of uses for users, for clinical researchers, for clinicians, but also billing departments. Another very major commercial application of NLP in medicine is on automatic billing. And then, of course, also fraud detection and analysis is another major commercial application area. Consumer health is another major area of use. This is sort of text written, with a lay audience in mind, as opposed to text that's part of a clinical practice. And so this might be for, consumers looking for what this thing on their arm might be, kind of queries, but also researchers who study how people who aren't doctors think about healthcare information. And then language produced by patients, right? So voice is a biomarker for diagnosis or treatment, using language as an input to an assessment pipeline, right? So if we have a language sample from somebody and take a language sample, say, once a month over a year-long period, we might be able to tell if there's been cognitive changes in that person, for example. Those are areas that are still developing, but have a lot of potential. So thinking more concretely from a computational standpoint, the kinds of computational tasks that we think about in biomedical NLP are things like entity extraction, classically. So here's a piece of text, identify all of the medications that are mentioned, all of the diseases that are mentioned, that sort of thing. And this is very analogous to entity extraction outside of biomedicine. So my example of reading a news article and extracting every name that's mentioned, maybe as step one to building an index for your newspaper kind of thing. Co-reference resolution is another classic NLP task that's very important in medicine. That's where you have an AFRA or indirect language and you need to link it up. So, it depends on what your definition of it is, right? Which it are we talking about in that sentence? Seen by cardiology, they recommended an echo in the morning, right? Figuring out that it was cardiology that recommended the echo. If you just look at the syntax of the sentence, it says they recommended the echo. Linking that back to cardiology recommended the echo is a classic co-reference example. And then temporal relation extraction. So did two events that you've extracted, which occurred first, right? What was the order? And that's very, very important in biomedicine, because frequently we want to find out things like, after this medication was prescribed, what happened, right? Or did this symptom start before or after surgery? Why is this interesting from a computational standpoint? Like, why would, of all the ways to do NLP, why is biomedicine so computationally interesting? It's because the medical context brings extra challenges. Everything is more complicated in medicine. We've got lots of polysemy and synonymy. There's a lot of ways to say the same thing, and a lot of words mean different things depending on the context. A lot of jargon and a lot of acronyms. So DRE can either mean dilated retina exam or digital rectal exam, and those have very different implications in terms of what was done to who, and also what the semantics of a positive versus negative result are. And so if you have a note that says DRE was positive, that doesn't actually tell you very much unless you know a lot of other stuff about what was happening. And then the documents we're working with are very complicated compared to what sort of garden variety NLP works with. So classical NLP algorithms are going to be like a newspaper article or a abstract or a tweet or an email or something fairly short, fairly simple structure, whereas clinical notes have wildly varying structure depending on who wrote them, where they came from, how they got there. They can be very long, they can be very short. Lots of domain-specific vocabulary as well that you're only going to find in biomedicine. And that matters because if you have a model that you've trained or developed to work on newswire text, and now try to run it on medical text, it's going to find that there's a lot of words it's never seen before, and so won't know what they mean, right? Because they're words that are only used in a medical context. To give you an idea of the scope of that, the Unified Medical Language System, the UMLS, which is sort of a central database of medical terminology, has, I have on here, 10.3 million unique English language names, and some of those are lexical variants of each other, but 3.8 million distinct concepts. Some of those are like normal ones that would occur in lots of situations, but certainly millions of those are things that you're only going to find in biomedical text. And then going beyond words, the syntax in medicine can be weird, right? There's going to be a lot of complex negation, no sign of edema, blood pressure was not elevated, no evidence of the absence of a negative finding, right? Like all kinds of weird, convoluted ways of talking, lots of passive voice. And then extra challenging is in medicine, the absence of something is often very important, right? If something is not mentioned in the note, in a physical exam note, for example, the reader of the note, another doctor, knows what could be, and they know the space of things that could have been mentioned. And if something's not mentioned, they assume that it was normal, right? That you're only going to document stuff that's abnormal. And so that tells you, if as the reader, it tells you something. For a computer, computers are very positivist in nature. They don't do well with absence of stuff generally. If I run my entity extractor over a note and it picks out 3 body parts, that's great, but it's not going to know about the 10 body parts that were also reviewed in the review of symptoms that they just didn't document because they were all normal, right? And so if I'm searching for people with a normal neck, in fact, the other day I was talking with someone about trying to identify patients who have never been pregnant or who have never had a child in the EHR. And that is actually surprisingly hard to do because in terms of the structured data in an EHR, when someone is pregnant, that of course gets documented. And you can have lots of different ways of documenting different things that can happen during pregnancy or conditions or events that are related to pregnancy. But the state of not being pregnant is like the default normal state, and it's very rarely mentioned. Like they wouldn't mention in my note that I have 2 legs, right? That's just not a thing that would ever get documented unless it was incredibly relevant for some reason. And so that's sort of philosophically hard from an NLP standpoint. And then other big challenges, there's a lot, heavy limits to the kind of data that we have to work with. We've all heard about the legally questionable and currently challenged practices of the big AI companies and how much data they've harvested from the web and from copyright holders and other things, terabytes and terabytes and terabytes of data. In medicine, we don't have that. We have one data set of clinical notes. It's a little old at this point. It's very hard. It's pretty hard to get access to, and it's about one hospital in one city and one service in the hospital. It's the ICU, and so that's it for everybody doing biomedical NLP for us to have in common. All of us have at our own research sites. We all have our own private data. We can't share it because of privacy and security concerns. So this is a major issue in the field. These restrictions make collaboration and make sharing challenging in some ways that other fields of machine learning and NLP don't have that problem, right? If you're working on newswire text, there's large amounts of text that everyone can use, that well-established ways to share it. There's no privacy concerns. There's copyright issues, but in the field, we have found ways to work with those over the years. So that's sort of why biomedicine's interesting from an NLP standpoint. So that's the what. Let's talk about how we do this from a computational standpoint. And there were sort of 3 main methodological epochs to NLP. The first is what some people call the good old-fashioned artificial intelligence era, symbolic representations of words and sentences and their meaning, and then rule-based and logic-based processing. And that actually could get pretty far. In the interest of time, I'm not going to get into that too much, but people actually made a lot of progress with that, and we'll see some examples in a minute. Then that led to the second epoch, which was using what we would now call traditional machine learning approaches. At the time, it was cutting edge, the latest, shiniest statistical learning methods. But now we look back and say traditional machine learning, where we come up with numerical representations of some kind and then use probabilistic learning and inference algorithms on it as though we were doing other kinds of statistics. And that started really in the 80s, led through the 90s, 2010s. And then in the last couple of years, there's, I'm being very, very like TED talky here. I'm calling it a third epoch. It's not exactly, but there are some differences in how we use what we're calling now generative AI to do NLP that I think make it from like a qualitative perspective feel very different to me as a practitioner than the way we did things under the traditional paradigm. And I of course should say that this is a very simplified taxonomy. I shouldn't have these as like three discrete things. It should be arrows between them because, even in the traditional machine learning era, frequently you would use the output of that as input to something with symbolic processing or the other way around. Now we're using generative things to feed back into the other ones. And so it's really more about three sets of tools. But as time's gone on, we've moved from like one being the most dominant paradigm to the other. And now we're sort of moving into a third that we're not even really sure how to characterize yet, but it feels a little bit different. So symbolic representations. The name of the game there is you think about your sort of level of linguistic analysis you need to do, find a way to symbolically represent that in the computer using discrete symbols. If you're wanting to work with syntax, you use trees. If you're wanting to use words, you have a code for each word, and now your word is a symbol. And then once it's in there, you can use logical operations to process it. This is an example of a little mini language for processing syntax trees for information extraction. And on the right, we have a pattern for extracting people's text that looks sort of like John's daughter Logan, extracting out the word Logan, or if it was another variation on that sentence. And this can get you pretty far, but there's some limitations to it that people ran into extremely quickly. So the first one is that language is what we call productive, meaning that there's always more than one way to say something, right? And so if you have a rule-based approach, you need to have a rule for every way someone can say something, and there's always an infinite number of ways to say something, so you've got this kind of hard philosophical limit. Some examples of the ambiguity you run into in language are some of these hilarious headlines, right? The squad helps the dog bite. Is it a victim of the dog bite that is being helped by the squad, or is the squad assisting the dog in biting the victim, right? Both are accurate. As humans, we can look at this and probably tell that, the drunk was not put in the violin case for 9 months. It's that, the drunk did something involving a violin that led to 9 months in prison, right? But a computer has a much harder time disentangling that. And we can't enumerate all of these. And that led to people thinking in the 70s and 80s, hey, let's see if we can use probabilistic approaches, right? And so the probabilistic approaches basically cast all of the problems, entity recognition, parsing, whatever, cast it as a probabilistic learning problem. So part of speech tagging, where we have a sequence of words and need to know which ones are verbs, nouns, adjectives, whatever, we cast that as a noisy channel decoding problem, right? We have a set of 5 inputs. We need to have a set of 5 outputs from some constrained set of tags. We have a probabilistic model that tells us out of all the possible outputs, which is the most likely according to some underlying statistical model, right? And once you sort of start looking at your problem that way, you can fit an awful lot of NLP problems that we used to do symbolically into that lens, right? Document classification is, finding the class that maximizes, that is most probabilistically likely given the input. Translation out of all the possible French sentences given our English sentence, which is it? Parsing is the same thing for trees. And so the story of NLP from like the, 90s really through about up until like maybe 5 years ago, 6 or 7 years ago, was basically how do we do that? Using what kind of models do we use? What kind of data do we use? Better and better and better models, but still the same basic approach. And what do we need to do this? We need data. We need large amounts of data, right? If you're doing translation, you need bytext, parallel data that is in both English and your target language. If you're doing spam filtering, you need a lot of spam messages that are marked as spam and a lot of ones that aren't, that are marked as not spam. Then you need methods to estimate distributions over that data, like any other statistical learning problem, right? So linear and nonlinear models, optimization algorithms, all the things you would do for any kind of statistical learning thing. You need ways to evaluate and compare them to tell if my system works better than your system, or if trying out a nonlinear model versus a linear model actually helps us or not. And that means having standardized data sets, standardized tasks, standardized benchmarks that we can all agree on. This is also part of why biomedical NLP has historically lagged behind the mainstream of the field, because that part was the hard part, or one of the hard parts. 1 and 3 were the really hard ones there for us. And then you also need some way to actually get your words into the system in the first place. And starting in about 2010 was when the big changes in the field started happening that led to where we are today with generative AI, because we found some new ways to get words into the computer that had some really interesting properties that I will not tell you a ton about now, because I also want to get to science. But if you take my NLP class, if we ever offer it again, we will talk a lot about that. Okay, so where does generative AI enter the picture at all? That third epoch, and of course what everyone's really into now. To get there, we're going to talk about language models. Before we talk about language models, I've used the word model a lot already, and many of you have not heard me rant about this yet. And for the people who have, I apologize, you're hearing it again. What do we mean by, what even is a model? Because I think it's important to actually nail that down before we talk about language models or large language models or generative AI. So a model, right, is a simplified, abstracted representation of a thing, right? There's a thing out in the world that we want to simplify and abstract and represent. We're going to shave off some corners, we're going to round off some edges, we're going to pick the most important things about it, and that's what we're going to focus on. And we're going to do this because there's a particular thing we're trying to do. And that purpose is going to inform what we chose to abstract. So that was very abstract. Let's get concrete. These are two models of an airplane, right? And neither of them is the airplane, right? They're both models of the airplane. We've taken all the complexity of a real airplane and we've changed it. We've made it smaller. We've also left out a bunch of stuff. Neither of these can fly. The one on the left doesn't have any paint, doesn't have any landing gears, doesn't have windows, right? But is very, very, very carefully shaped to have the wings be perfect, right? And the fuselage be perfect. It's for wind tunnel testing and aerodynamics, and it captures exactly the pieces of the airplane that are important for telling if it's going to fly or not, or if changing the wing this way or that way is going to affect its airworthiness. On the right, we have another model of an airplane, and this one is designed to help us all agree on what to paint it. That's also really important, and it has very, very high, fidelity to like where are the landing gears and how many windows are there and what part of the airplane and where does the stripe go. But it is not aerodynamically accurate at all. Neither of these is the right model or the wrong model, right? Like they're both right for something and wrong for a lot of other things. And anytime anyone's talking about a model ever in any kind of context, you should be asking yourself, okay, what are they trying to model? Who built it? What are they trying to model? What did they leave out? And is whatever they left out important for what I'm doing right now? And so let's now think about language and how we might build a statistical model of language and be thinking in terms of what we're going to throw away and what we're going to keep. So if I asked you to complete this sentence, right, I was late assigning the blank. One possible syntactically valid word that could come next is homework, right? Another syntactically valid word to come next would be purple, right? That would be a pretty weird thing for me to say. The first one, if you know me, is a very plausible thing for me to say. And so if I asked you which of these is more likely, without getting out your dictionary, without thinking too hard, you could probably say that A is more likely than B. And another way to say that is out of all the possible sentences I could say, the probability of me saying the first one or me ending the first sentence with homework is a lot higher than the probability of me ending the first sentence with purple, right? Now, we don't know how much so. We don't know what the probability of either one is. I'm being kind of sneaky here. I'm using the word probability, but we haven't talked about like what the denominator of that is, right? But if you, but just speaking very hand-wavily about probability, you might say the first is more probable than the second. So our takeaway from this should be that language is not random, right? And so that means that there's probably some useful way we could model it probabilistically and statistically. And in fact, when we talk about a language model, that is all we have. All we are talking about is a model that models the joint probability of a sequence of words. Sometimes we will use those in a less about the joint probability and more about the conditional probability. So computing the probability of a certain word given the preceding part of the sentence. That's that's all a language model is, right? When you hear people talk about large language models or small language models, that's really all they've got. We sometimes abbreviate this by writing it as, probably a word given some history of preceding words. So what's missing from this model of language? We don't have anything in there about the linguistic context. We don't have anything in there about what the communicative purpose of, why am I talking about that I was late with the homework, right? Nothing about who's writing or speaking. Nothing about my hand gestures or my tone of voice or anything. All these other things that are part of language we're throwing away. We're keeping one small part of it. So there's the great George Box quote about all models are wrong, some are useful. This is an example of a model that is both wrong and useful. It's wrong in that there's a lot of parts of language that a probabilistic word-based language model does not capture. But there are some useful things we can do with that model. So we can take different strings and we can say which is more likely than the other. Which might be useful if you have a speech recognition system, for example, and it's maybe making a top 5 guess of what it heard you say, and now needs to disambiguate, right? Which one is a more likely output, or if you're doing a translation and you just come up with 5 candidate translations, and you need to know which one is a more fluent one, you might think the one that has the most likely sequence of words compared to the other ones would be there. We can also sample new strings from this distribution, right? Which of course is what you do when you talk to ChatGPT, is it's drawing new words out of the hat using its language model. So how do we build a model like that? The easiest way is to count. You count words and you do a maximum likelihood estimate of their frequency. So if we have a sentence, its water is so transparent that, how likely is the to be the next word? Well, that's, POW given H. The maximum likelihood estimate of that is the count of how many times it did follow that word versus how many times we saw that word at all, right? If we do that, if we have enough data, we can actually count these things up. If you have 1 million newspaper articles, you go on them and you find all the times this longer phrase occurred, the shorter phrase occurred, you divide it out, you get an estimate. Problems with that, of course, is if we have a longer sequence, we might not have any examples of that exact sequence being said. And even for shorter sequences, we're going to very quickly run into a situation where our numbers are very small, meaning we don't have very many examples, which means we're going to get very unstable estimates, which will be not very helpful. So we can cheat. We can maybe say we don't need all of the history. If we think about our conditional probability thing, we can approximate a longer conditional probability using the chain rule. And we can chain rule ourselves all the way back down to only needing to know some certain window of our history. So like, let's say that we have, we decide we only need 2 words of history to decide how likely something is. This is called a bigram model. We only need to count up pairs of words. And now you can get away with a much smaller corpus of text and get stable estimates that way at the expense of accuracy of your predictions. So a really trivial example here, if this is our entire corpus, and we want to know the probability of a sentence starting with I, right? With a bigram model, we count up how many times did we see a sentence start with I, divided by how many times do we see a sentence start at all. We get 2 out of 3. There's a 2/3 probability that if we draw a new sample out of this distribution, it'll start with I, right? If we, oh, and of course, Sam following am, we know that every time we see am, we're 50% likely to see the word Sam after it in this tiny toy corpus. So how much history do we actually need to keep around to be useful, right? Because back to the models being wrong, some being useful. Obviously, too little history is not useful for anything, right? This is a unigram model that doesn't have any history and only knows about how likely each word is. And if you look at this, this was trained on Pride and Prejudice. We see that certain common English words like the are more likely to occur in this generated text, but overall it's kind of gibberish and doesn't make sense. 2 words gets us to something that is looking a little closer to language. 3 words is getting something actually quite closer to language, but still nonsense. 4 words, you have to actually read it to find out that it's nonsense, right? And you can imagine that as we get longer and longer, we're going to get more and more longer runs of text that go together because it's actually starting to reproduce whole runs of text that it saw during training, right? For a lot of things, this is actually good enough for a lot of purposes, but obviously not for answering questions or making ChatGPT. Counting is a pretty basic way to do it. Starting in the 90s, people started coming up with much better ways using other more powerful statistical learning approaches. We can use SVMs, we can use logistic regression, we can do lots of things. And then of course, also we can use neural networks. In fact, one of the first applications of neural networks to language was in a simple word prediction model, but it was kind of a toy example because they didn't have the computing power they needed then to do a neural network of any size. But very, very quickly, once we did have that computing power and did have modern neural network algorithms, we started using them to make first feed-forward architectures, then recurrent architectures, then of course transformers to do our language modeling. But fundamentally, they're doing the same thing, right? It's still estimating the probability of words in a joint distribution. It's just doing it using more powerful methods. And that brings us to large language models. So large language models, how large is large? The ones that we consider large language models today are having parameter counts in the billions to hundreds of millions to hundreds of billions of parameters. So that is a lot bigger. Like my little toy counting model there for Pride and Prejudice had like 100,000 parameters. So we're many, many, many orders of magnitude bigger. And when parameter counts get big, things get weird. In the Hunter S. Thompson, like, you know, the going gets weird, the weird turn pro kind of thing. When language models got to be that size, people pretty quickly figured out that they were having a lot of behaviors that were going a lot beyond what anyone had seen with smaller models. And that's sort of what kicked off the modern last 5 years or so generative AI boom was finding things that that when models crossed, depending on who you ask, like getting into the billions of parameters, they started having some different properties, then tens of billions and hundreds of billions, things got really weird. Okay, some differences between LLMs and the count-based ones. More parameters, what kind of history they represent. The little bigram model, the 3-gram model, like that only knows about 3 words previously. Big language models now go back thousands and thousands of words, right? So they can really have a much they can use information from 1,000 words ago to help decide what comes next. That's why they can make longer, more coherent output. The way they compute their decision rule is a lot more powerful than just going back to see what the most, you know, looking at our probabilities and taking the highest probability. Like they're actually doing much more computation under the hood for that decision rule. But the what is being computed is still the same. So why would this be the case, right? Why would it be the case that if you have a big enough language model, it would be useful for anything? If you think about how to answer these questions, I'm giving some sentences here where I've taken out a word, right? And being able to fill in what should go there, some of these require a fair bit of knowledge, right? Being able to say the Saturday market is in blank Oregon. If you can answer that, you must have seen somewhere those words go together, right? And similarly, if you take a model and are training it to fill in the blank, you're going to be basically teaching it that, hey, the word Portland is associated with the Saturday market and with Oregon. And if you do that on enough data with a big enough model for long enough time, it starts to absorb a fair bit. People talk about how it learns things. It doesn't really learn things the way that humans learn things, but it's certainly picking up a lot of associations and it's picking them up in a lot of different contexts. And we think about how those, in these kinds of contexts, those kinds of things start to look like, if a model that can fill in those blanks starts to look like one that could be useful for different kinds of tasks, right? Now, what didn't we see? The LLM is not a database, right? It's looking at pairs of words and memorizing them, but it's not like explicitly modeling facts the way a database does, right? And it's not a search engine. And that means that it's really hard to know what is or isn't in there, right? You'll notice I'm using a lot of weasel words about it kind of does this, it sort of does that, it might be able to model this, right? It's because we don't actually know. It's also not performing reasoning in the way that like a good old-fashioned AI symbolic reasoning model is, right? It's not applying De Morgan's law to help disentangle a logical thing, right? It is looking at associations and probabilities and picking out of the hat, which sometimes looks on the surface a lot like reasoning, but we'll see some examples of how that's not there. It also doesn't have a query syntax and also no delineation between form and content. So those are just both things that it's trying to learn. So a consequence of that, perfect consequence of that, the glue example from Google. When this happened, people very quickly traced it back to a Reddit post from 11 years ago, where somebody was trolling the original poster saying, I put glue in my, and if you know Reddit, you know that person is making fun of the poster, right? Google's AI crawling bot does not know Reddit. It saw a question, my cheese slides off the pizza. What do I do? Glue. right? And it only knows that there's an association now in its memory between pizza and glue. It doesn't know that that's absurd or any more or less valid than, having too much sauce, which is the actual answer to why the pizza, slides off. All right, so now let's take this intuition and let's have a medical example, all right? So I'm going to tell you now about some research I've been doing with Nicole Weisskopf and David Dorr and Leanne Michaels and Emma Young and the rest of their team. And we are looking at using LLMs to summarize clinical documents. And our motivation here is that in practice, the volume of clinical documentation can be very overwhelming, right? There's just so much documentation, especially for patients that have a lot of chronic conditions going on. Maybe they had a complicated hospitalization. There can be a lot to disentangle, and you might have not very long to figure out what to do with this patient, right? And that can lead to cognitive overload, which can lead to errors and also leads to a sort of ennui and burnout and all kinds of bad things. Now, informatics is all about getting the right information to the right people at the right time in the right way. And so our thought, not just our thought, I should say, everyone and their dog is working on summarization of clinical documents because it's a really, if it can work, would actually be incredibly useful. So the thought is that maybe that could help. So the scenario we're working in is care planning, specifically an inpatient to outpatient handoff. So care planning, you have a patient with a lot of things going on, many chronic conditions. They're working with a lot of different providers, a lot of different specialties, and care planning is a discipline of coming up with a plan to manage their care and make sure things don't slip through the cracks, because that's really easy to happen with a patient with a lot going on in that way. And Dave Dorr's team for years now has been working on this informatics platform to support care planning. It's called e-care plan, I believe, and it has all kinds of cool ways to help visualize and condense information from someone's EHR to help them figure out what's going on, but also help their providers follow along and help their care management platform system work. It works entirely on the structured data in the notes, so problem list, medications, procedures, all that kind of stuff. Totally ignores the notes, and we know that the notes are important, right? There's a lot of really important information in the notes. The clinical notes, they're a rich and vital source of information. Here's an analysis that I'm pretty sure this was Nicole's analysis. I took the figure from a grant we wrote, so it doesn't have a citation in it, but I hope I'm not completely getting it wrong. I'm pretty sure this one Nicole did. But it was looking at congruence between structured data, what was in the notes, and what patients actually said. And the main thing to look at here is I do have a pointer. Just the delta here, chart review means looking at the unstructured note. And we're seeing a lot of information, right, that was in the note. The patient, of course, in this case, the patient knew perfectly well, but the structured data didn't show that they were on aspirin, for example. And you can multiply this out by a lot of different things. My other favorite example is triple negative breast cancer. At least in our EHR, there is an ICD-10 code specifically for that now, but almost nobody ever uses it. Every single note for a triple negative breast cancer patient starts with, this patient has triple negative breast cancer and is here for whatever. But if you look at their diagnosis codes, they'll have the ICD code for malignant neoplasm of the breast, maybe also one for one of the mutations, but not saying that it's triple negative. And so if you want that information, you're going to the note. But the notes, as we all know, are poorly structured. They're very long. They can be repetitive. Copying and pasting is a real problem. So hence the idea to utilize LLMs for care planning. We had this idea, then we started digging into it a little bit and quickly realized that summarization is one of those words that means 50 different things to 50 different people. And it can mean a lot of different things. We went looking in the literature, found a theoretical model. This is the aortis framework from a team in Texas, but including former friends of the department, Dean Sittig and Adam Wright were on this one, or not former people from this department who are now friends of the department. And this is a conceptual model about all the different kinds of activities that fall under the larger umbrella of clinical information summarization. And so they have them ranked, sort of going from the most basic, so just aggregating quantitative data from multiple places to make an average or to make some kind of table, all the way to synthesizing new content, right? And they have it sort of laid out the steps that you would need to go through along the way. And we were thinking that we would be able to follow this framework to help guide the LLM, and you give it some scaffolding, and it's actually still what we'd like to do. In looking at it, this reminded us of another theoretical model from information science that we thought might be an easier place to start. And that is the DIKW hierarchy, which if you have not heard me rant about it yet, then you're about to hear it. So this is a really, really cool framework for different kinds of information. So at the bottom of the hierarchy is raw data. Data are just raw symbols. They represent observations, measurement, sensing, but they're totally devoid of context, right? Information, data become information when we include context, when we include things about when, who, what, where, right? If I just tell you, here is a blood pressure measurement, that doesn't tell you anything. If I tell you this is Stephen's blood pressure measurement from Tuesday at 5 o'clock, that tells you information, right? That's the difference between data and information. Knowledge gets us to how. Questions about how, right? How information is applied in a particular situation, a specific task is performed. So if you think about someone who's memorized a multiplication table, right? They know how to multiply the numbers that are in that table. Do they actually know how to generalize from that? Probably not, right? Insight, which is sometimes called understanding in the framework, gets to that question of generalization. It's about going from just knowing that you have all these facts and that you would use them to multiply numbers to going one step further and knowing how to multiply new numbers, right? And then wisdom is one more level. Wisdom is about why. It's about judgment and experience and knowing what the right thing to do is in a given situation. So a temperature measurement on its own tells you very little. A temperature measurement with the time attached and what the preceding one was might tell you that the temperature is increasing. All the way up to the end, you might know, okay, they have a fever and I should do this to fix it, right? These are all sort of different levels of knowledge. And as we were reading about the aortis model, a lot of these things kind of mapped to different steps in the aortis framework for summarization. Different kinds of summarization activities were more about aggregating data, linking data, all the way up to synthesizing with, combining with data from other sources, to be more generalizable, and so on and so forth. So we took a stab at it. We had two research questions. The first one was, how well can humans summarize discharge notes? Because we realized very quickly that we didn't actually have a good handle on what a good summary would look like, because this isn't a task that people usually try and do. And so we said, okay, step one, what if we get humans to do it? How well can humans do this task? And how well can they do it if we ask them to do it at different levels of abstraction or synthesis? And then two, how well can an LLM do it, right? And we asked this along a couple of dimensions, quality and reliability. So not just how well can they do it, but can they do it consistently? Because the models all the model output, remember, is just sampled from a distribution. So when you ask it to generate a summary, it could have generated 1 million summaries, right? Given that input, if you resample 1 million times, you get 1 million different summaries. And if sometimes it's really good and sometimes it's really, really bad, that's not actually useful, right? What we want to know is it consistently good? So our overall plan was we would have humans and LLMs write summaries of some discharge notes, then have the humans write the results in a blinded manner. Our outline looked like this. We started with a data set called MIMIC3, which is the one I mentioned earlier. It is from Beth Israel Deaconess Medical Center in Boston, from their ICU. It is the only publicly available data set of EHR notes. It's been de-identified. You have to go through some hoops to get it, but it is possible to get, and it's sort of the standard in biomedical NLP. And then we took a subset of that had been annotated for to have like certain extra properties in the notes, like particularly good notes. And then we filtered it to patients that had, we had a set of chronic conditions. We had some additional inclusion criteria to identify a set of 84 discharge summaries. We then had a group of internal medicine residents and attendings write summaries. Then we used Llama 3, the 8 billion parameter version, which is a very high performing modern LLM in a size factor that can work on reasonable amounts of computing power. They have a 70 billion parameter one, but we don't have the capability here at OHSU to run a model that big yet. We will very, very, very soon. And then we asked both humans and the LLM to generate summaries at 4 different levels of synthesis, at a data level, an information level, and a knowledge level, and a wisdom level. And we have definitions for all of those. And we evaluated on dimensions of accuracy, synthesis, succinctness, and usefulness. And we have definitions for all of those as well. The sort of synopsis of the instructions we gave at the data level were to basically focus just on summarizing underlying data points from the note. For information, we asked it to include relevant context about the patient and their conditions, as opposed to just listing diagnoses and medications. For knowledge, we asked the humans and the LLMs to try to incorporate information that they might have access to from various guidelines or what they knew about treating those diseases. And then for wisdom, we asked them to zoom out a bit and think about patient values and preferences and focus on more holistic needs of what that patient might need going on. So initially, as a feasibility analysis, We ran the LLM over 10 notes and asked it to draw 10 samples per note. So for each note, we had it generate 10 nominally identical summaries, but as we'll see, they varied quite a bit. And then we decided that if they were, and then we had a human rate them, and along those dimensions, it was very tedious to do. And if 4 out of 5 of the samples, if the sample was rated a 4 or a 5 on the Likert scale for a given criterion, we called that good enough, right? Fairly arbitrarily. But the way we set up the parameters for the Likert scale of 4 was like, there were things not ideal, but there was nothing wrong with it, basically. So 4 and 5 was good enough. And on this plot, what we're looking at is the percent of notes that rated that way. And so we see there's a lot of variation. Sometimes the model did a pretty decent job. Other times it generated notes that were really lousy. That was a little concerning to us. But what we did find promising was that most of the time it was a lot of the notes, 80% of more than 80% of the time it was scoring 4 or 5 overall. So that's, we thought that was like encouraging to be worth continuing with the experiment, but also the variability was concerning. For the final analysis, and I'm sorry if having this come on all at once, we'll walk through it. This is the comparison of human ratings, the comparison of how the human generated notes compared to the LLM generated notes for the experiment where we had humans and the LLMs summarize the same documents. So what we see here is for each of these are the 4 different levels of note resolution: data, information, knowledge, and wisdom. The dotted line is our magical 80% threshold. And on the left, we have human rating, human-generated, the scores for the human-generated summaries, and on the right, we have scores for the LLM-generated summaries. And what we basically found is when it comes to succinctness is where we saw the biggest differences. But data information, both humans and LLMs, humans had the edge by less, but they did have an edge, and things were okay. Where things went off the rails were with knowledge and wisdom, both for humans and the LLMs. And some of that comes down to less of a consensus among humans about what a good note should be, is kind of my takeaway from that for these kinds of these kinds of notes. But we also do notice a pretty dramatic difference along most of the dimensions, especially the accuracy dimension and the succinctness dimensions, where the AI was doing less of a good job in that regard. The accuracy is the one that I'm personally the most worried about with all of this. And like, it's here, this accuracy is okay. That accuracy is not okay, right? So what we see here is that the AIs have some work to do, but they did produce useful summaries in the knowledge domain. But the information ones, they kind of struggled. But forget the quantitative assessment for a minute. Let's actually look at some qualitative assessment, because it's easy to look at this and say, like I did a second ago, oh, hey, that's basically okay. And I'm here to say that it is not basically okay. So here's an example, and I can't show the whole note, but it's de-identified, but there's a data use agreement, but I can show like a little snippet, and I think I can show a summary. So this is a summarized data summary, and this is a patient who had carotid artery occlusion and was there for stuff, and they had all kinds of heart problems and whatever, and here's the summary that it generated, right? This looks pretty reasonable. And this one actually scored pretty high along some dimensions, but take a look here. It says they was discharged in stable condition on Coumadin. That actually sounds pretty reasonable, right? People that have cardiovascular stuff going on, it's normal for them to be on Coumadin or something like that, especially after surgery or whatever, because there's clots, right? But let's look at his discharge medications. His discharge medications do not include Coumadin at all. There is no Coumadin. He was not on Coumadin. Now, when he showed up, he was on Coumadin. His medications at home were on Coumadin. In the long note, it talks about how they stopped his Coumadin. So the note, the summary basically made something up. And it made something up that is unfortunately very plausible, but it is wrong. So when people talk about hallucinations or confabulations, sometimes they're talking about hallucinating something totally ridiculous. This is an example of, you know, if it had like hallucinated that now he's on some like chemotherapy medication, or there's something totally out of bounds. This is hallucinating something that's actually completely plausible, and in fact, was at one point true for the patient. So that is really insidious and bad. And when we look at the other samples from that note that we had the computer generate, it found different ways to get this wrong. You know, it even said it was notable that he's on Coumadin at the time, and used is as opposed to was, right? Sometimes it said the patient was, other times it said it is. There was a lot of variation. Here's another one. It explicitly says the patient is taking Coumadin, whatever. Notice that it also doesn't mention the Percocet, which feels relevant because it's an opioid, but I'm not a doctor, so maybe that is something that would be elided in that list. We had a lot of discussions in our team about like how, you know, one of the frequent annotations on this from the human annotators was like, why did it choose these medications and not those medications, right? A human summarizing, you'd have some thought process as to what to include or not include. The machine was pretty random what included, and also made up stuff that shouldn't be there. So 3 out of the 10 samples from this one were just wrong, like made up, basically gave the wrong thing. And one of the other ones was arguable, like it could be interpreted either way. One of the I summaries actually like goes further. It doesn't just say he was discharged on Coumadin, it actually makes up that after the procedure we put him on Coumadin, which is like the opposite of what happened. 4 out of the 10 I samples were wrong about that. So that's very bad. Here's another one. This is a different patient. Look at this last part here. Notable vital signs were baseline oxygen saturation of 92%, and poor, you know, on admission. But on admission, the oxygen sat was 80 to 88, and then they got up to mid-90s once they were on oxygen. Later in the note, it says something about a past medical history where they did a baseline oxygen sat measurement and got 92%. But 7.5 out of the I'm giving 1.5 points because it was arguable whether it was saying that at some point in the past she'd had 92% or whether it was saying on admission she had 92%. But like basically most of the time it gave the wrong thing about the oxygen sat, and I don't know if 88 to 92 is that big of a deal, but it definitely is a problem that it is not accurately summarizing and is doing so in a way that is very, very, very clinically plausible and problematic. So in summary, what we learned is that LLMs can in fact generate very reasonable looking summaries that include mostly accurate information, but they're what I'm calling stochastically inaccurate, meaning you're rolling the dice, right? Sometimes it's right, sometimes it's wrong, and in no actual informatics tool would we have it generate 10 summaries and make you read all 10 to see if they agree with each other. That would defeat the point. So that is problematic. So anyone seen The Good Place? This is like Derek, as opposed to Janet for our AIs. So where do we go from here? I think improved prompting techniques for using the models, this goes back to the 3 paradigms of NLP. Like part of what we're doing in this 3rd paradigm is figuring out how to get good output out of these models. And I think there's some techniques we could use to help that might help with this. However, one of the other takeaways, evaluation is really critical. Our evaluation method numerically masks this problem, right? We have a table, we have a graph that looks like it's fine most of the time, and that's masking the fact that when it's wrong in ways that are bad. So evaluation is really important. Looking at your data is really important. Coming up with ways to measure these that actually gets at this. And I think the fundamental problem is that LLMs are LLMs, right? These behaviors that it's doing are pretty ingrained in the architecture. Like it doesn't think it's summarizing. It thinks it's producing a plausible looking output, which it did, right? It made a plausible looking output. You know, we think we're asking it to follow instructions. We think that's what we're training it to do. The model doesn't see the world that way. The model is trying to recreate its training data in a plausible way, and it doesn't really, it says, what do you want? Like Coumadin was mentioned. Coumadin is a normal thing to be discharged on. Close enough, you know, like it's, so we might have a little bit of a mismatch of our tool to our use case here. So with that, I have 40 seconds left. So with that, I will stop and I will take any questions anybody wants to ask about this or anything else. So. I know it's kind of a downer to end on, but Phil.
For the discharge summary project, did you ever evaluate how often humans were wrong?
So that is the something else that we have not yet done, but we would like to. Yeah. Well, wait, that's not true. We did evaluate quantitatively, right? We evaluated them. The red lines are for accuracy. So we did look at accuracy. and they were higher. I don't have data, and I don't know if Dave or Nicole are on the line. They might remember, or might have that data, or know if we looked qualitatively at what kinds of errors were made. But that is very much the next thing we need to do.
Because that Coumadin error is like, it's like that could definitely happen.
Yeah.
You could definitely see someone try to get a discharge summary out half the time, do a quick scan, and then pull that information wrong.
Mm-hmm.
You can do that just easy to see it happen.
That's slightly reassuring and also slightly not.
Well, the thing is that all these notes are going to be like looked over again.
Right.
Like, so
Well, in a patient care planning thing, the whole point is they might not be. The whole point is that this might be what your care management person sees and uses that to guide like what happened during their hospitalization last week. Maybe they'll go back and read the whole thing, or maybe they won't. So that's that actually is a good point about like how we would use a summary in practice would be important because humans could make similar kinds of mistakes. Yeah. Any other questions?
There's a question online.
Yeah.
Ryan Grattan.
Mm-hmm.
How do you manage copy paste or repeated information, especially if no longer relevant?
Yeah. Oh yeah, that'll totally mess it up. Yeah. So the question about copying and pasting, how copied and pasted text would affect what a model would learn, it'll totally mess it up. The model doesn't know, right? Yeah.
Why didn't you guys set the bar at 80% for accuracy, especially if we're talking about medical data, which is sensitive?
Arbitrary. Yeah, pretty arbitrary. Like, we're not saying 80% is like you're totally good to go. But we were figuring that was like good enough to be worth like thinking about further. If it couldn't even make 80%, that was gonna be a real problem. 80% we figured we could maybe try and fix the last 20%. I'm now questioning that, or rather what I'm questioning is what other metrics we might need. Yeah. And I should say that the humans rated those ones that had the Coumadin errors, they rated them very low for accuracy. So like our evaluation method did catch that those were low. But in practice, the fact that that's the kind of error the model does make a non-trivial amount of the time is kind of worrisome. But our human raters did catch it, which is good. But any other questions? Okay. Well, if there's no other questions, thank you everyone for coming and for listening and for letting me practice talking about new research on you guys.